Okay, so I think I'll start with the lecture then. If there's no questions, anything, please interrupt anytime. Okay, so today, right? So last week we spent some time doing definitions on finite frame theory just to sort of understand these objects. Today we're going to start talking about parsimony, right? So the idea here is that I mean, won't for now I'm more just talking a bit and won't write much. But so parsimony is the idea that the data or the things that we want to recover have structure. Right, so a very good example is the matrix completion problem in recommendation systems. Right, so one example that I already talked about a bit was recommendation systems. Right, and so in recommendation systems and the so-called Netflix prize, for example, right, and so you would have, say, maybe items, a matrix with items and users. Right? And what you want to learn is you want to learn this matrix where this entry, maybe it's a score. Right? You can see how this is very useful if you have, say, an online shop or something like this. Right? If you are able to, you have some users of your website, say, you have some items that you're trying to sell, and if you knew the matrix of scores, how much each user likes an item, then you could make very good suggestions. Right? But in reality, what you have is some users rate some items. So one has, right? So one has some entries of this matrix, and wants to learn the rest. So we'll talk a bit about this. It's to learn the rest. Right, so this problem is known as matrix completion. These types of things are very common in data science, machine learning, signal processing in all these fields. And so how does one, you're faced with a problem like this. How can one go about answering this? So if I give you, say, right, let's say that I get maybe a 5, a 1, a 3, a 4, a 2, let's say it's a rating from 1 to 5, a 1, and so on, right? How do we go about filling the rest? If this matrix had no structure, there's no way we could do that, right? But probably you would argue that if this, right, if you would see something like this, 5, 5, 1, say 1, and then you see another user, 5, 5, 1, 1, and then it asks, what do you think is here? You would probably guess, well, in that question mark, probably it's a 1 because these two users seem to have very similar tastes, right? And so there is a sense in which we believe in some form of parsimony, right? The data should have some kind of structure, right? This, like, the simplest explanation for something is probably the most likely to hold, right? And so we have to capture somehow the fact that these things that we're learning, these objects that we're trying to recover or learn, are simple in some form, right? So we need some form of parsimony assumption, right? And so here, like, right, the word that floats around a lot, right? This is like Occam's razor type thing, right? And so here, the assumption is that this matrix, let's call it M is low rank. Right? So this is the assumption. And now that you have this assumption, so people who deal with these score matrices and so on tell you these matrices tend to be low rank. Now that you know it's low rank, it makes sense that there's only maybe, like, if it's rank 5, means there's, like, essentially users are described by 5 degrees of freedom. There's sort of 5 different types of taste, and you have a linear combination of those, right? And clearly these two seem to have very much the same kind of taste, and so it would be a reasonable thing. But now I can ask, when is it that I can recover a matrix that I know it's low rank from some measurements of it? Okay, so we'll go back to this next week in the last lecture of this part of the course before the break. But I'm going to talk about a different kind of parsimony, which is actually very, very related. And most of the techniques that we know for matrix completion and Netflix problem and so on, they come actually from this other, they come motivated from techniques for this other form of parsimony. And it's a lot easier to describe, especially since we're doing most things in this part of the course deterministically. And sort of, I'll try to convince you in the last week that actually most of the ideas carry through, but we're going to dedicate more time to sparsity, right? So another instance, right? There's many forms of these types of imagining that what we're trying to recover as some structure or learning. Another form is sparsity. Right, so this is very popular in I don't know, in signal processing, right? Very popular in image processing, in communication theory, and a bunch of other, and even in statistical regression, right? In statistics, you'll see in statistics class that when you try to do, say, regression in statistics, that it'll make a lot, like you're much more convinced by your regressor if it has very few non-zero coefficients, right? If your prediction depends on very few parameters of your right of your variables at your like your x, right? And so and so this is the and so people in statistics will try to find regressors that are sparse, right? And the way they do this is exactly by solving a problem that will come motivated by what we're going to explain here. So I don't want to spill the beans just yet. So I don't want to say how you will find such sparse regressors, but we'll see here in under the more in the context of signal processing, but it'll be exactly the same kind of approach, right? And then we'll also motivate an approach for the matrix completion problem. So the idea that I'm going to now use a bit the word of image processing and signal processing and so on, that many natural signals, right, or images are sparse in some appropriate bases. Okay, so and there is a Jupyter notebook, like in the if you go on the forum, there's Jupyter notebooks that are there to accompany the class. There's one that shows exactly this, where if you have an image, so I mean, you probably have done this experiment before, I've seen it at least, where if you take a picture with your phone or with a camera, and you go and you try to save it in an encoding that saves the value of every pixel. So I think a common one is called BMP, right? It occupies a lot of space on the computer. But if you solve it normally as a JPEG, for example, it occupies a lot less space, right? The image gets compressed, but when you look at it, you can't even tell. So basically what happens, what is happening exactly there, JPEG is quite simple. All it's doing is it's writing your image, right? You take an image, let's say I take an image X, a vector, let me say that the reals, right? So a vector in Rn for very large N. I'd say n maybe is number of pixels. Okay, I'm gonna do some math in a bit. There'll be like 20 minutes of this description, and then we'll get into some actual math. But I want to first motivate all the things I'm gonna do. All right, so let's say we have x in our n for very large n. Let's say the number of pixels. Okay, but it's written in a basis, right? So it's not true that most pixels are zero, right? If I'm taking maybe a picture of the night sky or doing astronomy or something like this, that would be true that most pixels maybe are just zero, they're just black pixels. And then what I would do is I would maybe instead of storing the whole image, I could just store the location of the places that are not zero, where the stars are or something like this, and this would be much, much cheaper. But it turns out you can do this with essentially any image. Right? Not, of course, in the basis of the pixels, but once you write it in the right bases, which usually are the wavelet bases or even the Fourier bases on blocks, like X is very sparse, right? When written in an appropriate basis. There's, of course, a lot of work in trying to understand what is the right basis for images and for signals and so on. And a lot of machine learning also helps there. But let's say here that we know the basis. Okay, so what I mean by x is very sparse. Let's suppose that x is already the coordinates of the image in the right basis, that x has, say, has at most s non-zero entries. Okay, so we often use this word, which is a bit of an abusive notation, or a lot of an abusive notation. We call this the L0 norm, right? Warning, this is not a norm. Okay, but we use it nonetheless. Of a vector, L0 norm, we call this the number of non-zero coefficients. Okay. And so if you have a vector, right, you take a picture with many, many pixels. Now in appropriate bases, let's say x is already the coordinate of those bases, it's very sparse, right? And so this means that you don't actually need to save all those zeros. You could just save the locations of these non-zero entries and their values, right? So things like JPEG, and in particular JPEG 2000 and so on, they work exactly by exploiting this. Essentially, dropping the zero entries on a sparse representation. Okay. Now, there's many ways why one would want sparse representation, right? One is compression, right? I mean, if we had to imagine if we had to save all the pictures, every single pixel value, right? The phone memories and all this would need to be a lot bigger. I mean, JPEG makes our life a lot easier for sure. But there's other reasons, right? So if you're trying to learn rules, like in regression, right? Learn prediction rules, as you'll see in the second part of the class. If something is sparse, you sort of probably believe that if it's still fitting the data, it's more meaningful, right? It's the whole principle of Occam's razor and so on. But there's another, so an observation that was at least mathematically done somewhat recently is that there's another benefit to this, right? If you think sort of, I mean, almost philosophically, but practically about what's happening here, when your phone takes a picture, it's taking all these pixels, like 12 megapixels or whatever many millions of data points, to then actually change the basis to this JPEG basis, drop all the zeros. So in the end, it's saving a lot less, right? In the end, the JPEG is saving essentially around S coefficients, which is a lot smaller than N. So why did we go through the trouble of taking all these measurements when actually, after a change of basis, we're actually going to drop most of them? Right? It feels like a very suboptimal thing to do. And so this is the key idea behind something called compressed sensing, right? Which is sense. I mean, I'll write sort of the key idea, but since we will drop many coefficients, could we have measured less to start with? Okay, I'm being very vague, but we'll make all this into math very soon. Okay, and this is the idea of compressed sensing. It's a beautiful mathematical topic that motivates a lot of really interesting math, but then has applications all over the place, as we'll see, for example, in recommendation systems. I mean, it won't be clear yet, but it will be clear next week. Okay, so this is the idea behind compressed sensing. And the point is that, maybe for the phones and so on, like it's quite cheap. The cameras or like taking more pixels or something is not so expensive. But there's cameras, of course, for like other types of light in which it's quite expensive. And so if you could somehow measure less, that would be a lot better. And so there is a prototype called the 1 pixel camera that uses this type of technique and so on. One place where this is really important and really useful is in, for example, MRI. Like very useful in, say, right, maybe I should mention in MRI. So there's very nice articles about this, like even like popular science type articles. The point is that if you can measure less, say when you take an MRI or something like this, then the people need to be a lot less time in the machine, right? And nobody enjoys being inside those machines. So if you can have people be less time, then this is better. But not all, it's not just the fact that people enjoy it or not. There's some medical imaging where you might need to slow down organs or maybe the heart, or you need to stop the body in some way so that you take good images. And if you, right, then it's clear that if you need to stop the heart to take a picture, you definitely want to do this as little time as possible, right? So this has actually a lot of applications, and now there's actually machines that use this technology. Okay? And even though, right, I realize that at this point it might not seem that this is the same problem. It turns out to be quite similar, right? Because here we're trying to recover a sparse vector, right? Once it's in the right basis by taking very few measurements of it. Above, we're taking to recover a low rank matrix by taking very few measurements of it, right? Low rank is not the same thing as sparse, but it's being sparse in the singular values being sparse, right? And this type of intuition will actually help us a lot, right? But let's try to formulate this now mathematically. Okay, and there's of course many others. Like when you do things like topic modeling and so on, you believe that there's some underlying matrices not only are low rank, but they should be the product of two matrices that are, say, have negative entries and things like this. So by knowing a lot about the structure of what you want to learn, or the signal you want to recover, the representation you want to learn, right? In different fields, this has different names. You can then understand how many measurements you need to do it, what algorithms can do it, and so on. Okay, so now let's go into more precise mathematics. So the idea is, to be more precise. So given, okay. So okay, maybe I should make this clear. Everything will be the same for reals or complex, right? So we're going to use reals or complex. It's the same almost every time. When it's not, I'll make this clear. And so we use this to mean either. Right? Just because it doesn't really matter, and the theory works essentially for both, except in some specific things. Sometimes it's important to have one or the other, and I'll make this very specific. Okay, so then compressed sensing. Okay. I'll write it in English, and then I'll write it in math, like with math expressions. So when can we recover, right? So here we use the language of recovering. There's a vector and a known that we're taking measurements of and we want to recover. Recover x in, say, right? So okay, n sparse, an s sparse vector from d potentially much smaller than n measurements, particularly linear measurements. Okay, so how should we think about this? There's a matrix, the matrix phi. This matrix represents my linear measurements. Okay, I'm using the same notation because I'm going to think of the columns as bases. Right? This is going to be a matrix D by N. Right? So phi again, and K. I mean, hope this doesn't create confusion using K. I just mean to either reals or complex. It's all the same. Right? And okay. So this is my measurement matrix, right? Measurement. Okay. And so my measurements are obtained by y equals phi x. Okay. Okay. So, and I think y is a lot smaller. So y is, let's say, d-dimensional. So d-dimensional. Right? And we want d to be smaller than n. So the question is, when can we recover x from y, right? And let's write here the the matrices where we have the sizes. This is y, dimension d. This is short fat phi, which is d and n, and this is the vector x, which is n. Right? So we're talking about an underdetermined system. Okay, so how can we solve an underdetermined system? Of course, we can't solve an underdetermined system. There's many x's that would give you y, right? But on the other hand, we know that x is sparse, right? So we want to ask, when is it that, if we know that x is sparse, when is it that we can find x just from y? Okay, is the task clear? If not, please ask question. Right, we know, the point is that we know x is as sparse. Okay, and we know when we can do this, right? We're taking compressed measurements because we're not taking x as n degrees of freedom, but we're taking only d measurements with d potentially much smaller than n. Right? We know that we cannot possibly solve underdetermined systems, right? There's many possible solutions. Okay, we could try to do least squares or something, but it's not clear that that's promoting any type of sparsity. Right? How do we find x, a sparse solution to this system? Right? And when is it that it actually corresponds to the, if y is equal to phi x, when is it that there's only one sparse solution, basically? Okay, so what's the obvious thing to do, right? So the system is underdetermined. There's of course many solutions. So the natural thing to try, right, is what? Is to take the sparsest solution of this, right? Is to try the minimum, right, of the zero norm, such that, not a, sorry, phi z equals y, right? Of course, for y equals phi x, right? Y are my measurements. X is my unknown and y is my measurement, right? Okay, let's call this the L0 for now, for the sake of this lecture. Okay, so the question we want to ask ourselves, right? So the central question, I mean, it won't be the central question, but a central question is, when is it that solution to L0 is x? Right, and in particular, when is it that the unique solution, right? Because if there's two, then I'm really not solving anything. Right, if then at the end of the day there's two possible images, I mean, that doesn't help me very much, right? Okay, so I'm going to answer this question, even still before the break. But before that, I want to just say a few words about another way of thinking about this, right? Since this first half of today's lecture is a bit less, there's a bit less actual math, and it's more about giving some intuition, motivating these things. There's another way of thinking about this, right? So we'll answer this question in a second. But there's another important way of thinking about this, which has to do with dictionaries, right? So we can think that we have, so another perspective, but we'll give exactly the same thing. Perspective, it has to do with dictionaries. Okay, so maybe, as we saw before, phi is, right, will be we'll have a frame, right, will be a collection of frame elements, right? So here we change the notation somewhat, not a lot. Okay, just to be closer in spirit what we usually do in compressed sensing. So we can think of this as right as a frame, right? Another word for this is a redundant dictionary. Right? It's exactly the same thing as a frame, right? It's just a way to write a spanning set of our space, a way to write a bit, sort of a basis, but not really a basis because there's more vectors than dimension, right? But a dictionary is just now for any point y, for any vector y, any signal, any image, we can write it always as a linear combination of these vectors, right? Let's say that it is a frame, right? So it spans the space. This means for any, right, for any signal, I mean, I'm using signal as a sort of a very broad term, signal y, right, d-dimensional, again, let me use this, right? We can write y equals, right, as a linear combination of all these bases, of all the frame, or the dictionary, right? Right. I can write, right, a very popular dictionary is wavelets, for example, right? This is exactly how JPEG 2000 works, right? In the Jupyter notebook, you can go and there's a code. You can even try this in a couple of images there, and you can see what it looks like in the wavelet dictionary, like how the terms look, and see that there's a lot of zeros and so on. So I highly recommend going and playing around with a bit with it, right? But so I can write it in this way, but because it's redundant, right? Because it's redundant, you can do this in many different ways, right? Potentially, in right, potentially in many different ways. Right? Because it's a redundant dictionary. So how do you pick the right one? Right? A very natural approach and very common approach and useful one. It's natural to ask for the sparsest one, to be able to write your signal, your image, as the smallest possible number of dictionary elements, right? As a linear combination of the smallest possible number, right? You can see how this has many, right? It will give you ability to compress and so on, but actually it also allows you to denoise, allows you to do a lot of things. So a natural goal in redundant dictionaries and so on is to try to write, like find the sparsest representation. Okay? And there's a whole field of dictionary learning in which you get, if you give me lots and lots of signals, lots and lots of images, I try to learn what is a redundant dictionary such that my images can in general be written as very sparse linear representations in this dictionary, right? This is a whole other field that I'm not going to talk much about. Here I'm assuming that you know the dictionary, like this is given to you, but there's another field in which you try to find the one that best represents your element as sparse vectors, right? It's a very interesting and somewhat difficult problem. Okay, and so if you ask for the sparsest representation, you're exactly asking for the same thing, right? You're asking for the minimum spectral norm A, spectral norm, one norm, zero norm of, zero norm of alpha, such that, right, what is this exactly? This is phi alpha equals to y. Right? It's exactly, right? This is precisely the same thing, same as L0. Okay, so now here there's nothing necessarily to recover and so on, but this will make an appearance. Okay, so now let's try to answer the question. Okay, so when is it that the unique solution to L0 is x? Right, so I have, okay, so let's write this again. So I have y equals phi of x. Okay, we know, I mean, maybe I should put phi, right, is a short fat matrix. Okay. Now I ask, again, my L0, what is it? It's just minimizing. Oh, sorry. Z equals Y. Okay, so first theorem of today, or I guess a proposition. Okay, and we'll start using some of the ideas and definitions and so on that we did last week. So if X is as sparse and the spark, right? Remember the spark was the number of columns, the smallest number of columns that you could, the smallest, the set, the smallest number such that there is a set of columns with that number that's linearly dependent, right? So if the spark of phi is bigger than 2s, okay, then x is the unique solution to this problem L0. Okay, so already seeing how there's, okay, so the proof of this theorem will actually be almost trivial. Once you see it, you'll see that it's almost trivial. But there's a lesson already here. First of all, that potentially it is possible, right? We're already seeing that potentially, I mean, we can probably create, right, matrices that are short fat that still have a decent spark. So potentially we can actually be able to recover very sparse vectors from very few measurements, right? So if you think in particular of S equals 1, right, then all we need is for there not to be two columns that are multiple of each other, right? Because if I know that the vector I'm going to hit with phi is one sparse, only has one non-zero entry, then it means that the resulting measurement y is just a multiple of a column of phi, right? And so if it is a multiple of a column of phi, then I just have to finding, right, x is just about knowing which of the columns showed up. I just need them all to be not, none of them to be a multiple of the other, right? But there's already something here, which is that the design of these matrices phi, if I want to build a good camera that is able to do things with less measurements, I have to be able to design very well this matrix phi to have, say, large spark, right? And as we're going to see, low coherence too later on. Okay? But so let's prove this. Okay, let's just prove this by contradiction, right? By contradiction. Okay. Suppose there exists Z also as sparse, right? So such that the sparsity of Z is smaller or equal than S, such that um, phi Z is also equal to I. Okay. Right? This is if X is not the unique solution to this, then there must exist another Z whose sparsity that has less or equal than S than zero entries. Right? And so now, okay, so what does this mean? Because phi Z is Y, then I have that phi, right, Z minus X, right, is equal to Y minus Y is equal to 0. Okay, so Z minus X is in the kernel, right, is in the null space. Yeah, we use kernel and null spaces interchangeably. Then Z minus X is in the null space of phi. But what do we know about the sparsity of Z minus X, right? So what do we know about the number of non-zero entries of Z minus X? right? So if I have a vector with has at most s non-zero entries, I subtract by another vector that has at most s non-zero entries. The most I can get non-zero entries is 2s. Right? So for sure, this is smaller or equal than 2s. Okay, I mentioned this wasn't the norm, but I didn't say why. I mean, in particular, if I multiply, right, if I have a vector that's too sparse and I multiply it by 2, it's still too sparse, right? And so when we define norms, we like that the norm also grows by, yeah, this way. Okay, so this is smaller or equal than 2s, right? But now what does it mean for phi z minus x to be 0, right? It this, if you think about what's going on here, right? Let's say, I mean, I don't know how much detail I should use here, but clearly the spark of phi needs to be smaller or equal than 2s, right? Because what is this? This is a linear combination, right? This is a linear combination, or I should say a non-zero, non-trivial, as in like z minus x is not zero, non-trivial linear combination of 2s columns of phi, right? Right? Think about matrix multiplication. I have phi, right? Let's see, let's do a picture. It's nothing like a good picture. Right? This is z minus, okay, let me see. This is z minus x, say here. Right? Let's say it has a non-zero entry here, 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 here. Right? Let's say s is 2. Right? It has this 4 non-zero entries. This means that it's effectively building a linear combination of these columns, right? This one, this one, this one, and this one, right? Because if you think of matrix multiplication, it's just the sum of the columns of phi times whatever entry was here, right? And so in particular, it means that these 2s columns of phi are linearly dependent, right? So these 2s columns of phi are linearly dependent. Okay, and so this is a contradiction, right? Because we said the spark was bigger than 2s, so we have our contradiction. So it's proved. Okay, so now a question, and maybe I'll let you think a little bit about this. How large can we make the spark? So we want to make the spark very large, right? Okay, so think a bit about this. So in the homework, there'll be a question about this. Okay, but now it's clear that if we want to be able to have a unique, at least a unique, right, the measurement process is able to, at least in theory, to recover the true signal. I mean, we haven't yet argued that this is stable or computationally efficient or anything like this, but we need at least the spark to be large, right? We need the matrix phi to be injective on the set of S sparse vectors, right? And so now we can ask, how much do we need, right? How many measurements do we need, right? So this will be a question in the homework. I mean, formulate in a different way, but you should now, when you go do the homework, you should think about it this way as well. But if you think now about, right, because I don't want to start with any theorem in the last 5 minutes, but if you have phi, right, and I have x as sparse, right, this is n, this is d, I argue that I need d at least as big as s, like at least. Right? Why? Because, right, even if I had a fairy, if I had a little fairy that would come and tell me what entries of x are the ones that are non-zero, they say, oh, it's this one, this one, this one, and this one. I'm still solving a linear system where now I don't have any extra information because, right, I know where the entries are in zero, but I don't know the values of them. I would still be solving I would still need D measurements to learn each one of these entries, right? So it's definitely clear that D should be bigger or equal than S. Okay? But now the question is how, yeah, can we make it potentially, we can still make it much, much smaller than N, right? So what you should keep in mind is N is much, much bigger than S. Right? We know that D is bigger or equal than S, but can we have, right, can we have D still much, much smaller than N? While of course being bigger than S, or at least bigger or equal. Okay, so I have three extra minutes. Maybe I can do a back of the envelope calculation that maybe will be a bit advanced, but for those of you that have seen some of these things, you'll get this back of the envelope calculation. And for those of you that haven't, don't worry if it's not so clear. I'm happy to stick around in the break to answer questions about it, but it's not sort of so important for the course. But just to see what we expect, let me just do a back of the envelope calculation, and we'll prove some actual interesting theorems about this. Right, so non-rigorous back of the envelope calculation, just more as a side note because I have two extra minutes. So this rarely happens. Um, let's assume, okay, I'll do this very fast, but let's assume that entries of x were plus or minus ones. Right? Let's say that x was binary when it's not zero. Right? Then how many possible signals are there? How many different signals are there? Right? How many different ways I need to pick the support? Right? I have n, choose s. I need to pick where the support is going to be. Right? And then I have to pick plus or minus ones for each one element in the support. So there's roughly n choose s times 2 to the s different signals. Right? Let's say that each measurement sort of, right? Each measurement should roughly, let's say that our measurements are just say modulo 2, they only give me positive or negative, right? And this means that each measurement should cut my search space roughly in half, right? I mean, I'm being extremely hand wavy and this is not a proof. And so if each measurement cuts search space in half, what we would need is D to look a bit like logarithm of this, right? To the S, maybe I should move this. Okay, this is not, again, this is not a rigorous thing. I'm just giving it as an extra. Okay, so what is this? Okay, now if you're used to computing some of these things, these are just, oh, sorry, having trouble. Right, this is just what? This is logarithm of n choose s plus logarithm of 2s. Okay, and so, logarithm of n choose s turns out is roughly s. Okay, roughly as in, if you think about like Stirling's formula, it's roughly s log n over s. And then logarithm of 2 to the s is just s, so it's a lot smaller. So it gives a suggestion that, again, a suggestion, this is not a proof at all, that you would need roughly s log n measurements. Okay? So turns out that this back of the envelope calculation is in a sense correct. It's possible to do to recover sparse vectors with just s log n measurements, with D being something like s log n. Right? We will not be able to do this in this course because we don't know how to do this deterministically. Actually, this is the source of many interesting open problems. We'll do it at s squared, but it's still potentially much better than n. And so this is what we're going to do the next, maybe an hour, the next hour and a half. Okay, and this type of back of the envelope calculation that is not really part of the course. It's just as an extra because I had a couple of extra minutes. This is sort of the basis behind like information theory and looking at there's ideas of information theoretical lower bounds and counting entropy of the number of solutions and so on and so forth. Right? These types of arguments basically go back to like, Shannon and information theory and so on. Okay, so when we're back, I'm going to actually say something about when it is that we can recover this. Okay? And we will not get S log n, but we'll get something still quite good. And I'm happy to stick around to answer any questions. Right, so this is green is not really part of the course. It's like an extra, it's like an information theory perspective on this thing.